Between skyrocketing feed costs and tightening mandates for antibiotic-free production, modern livestock operations have zero margin for error. Surviving in this environment requires extracting absolute maximum efficiency from every gram of feed. Yet, producers consistently waste massive portions of their additive budgets by treating yeast as a single generic ingredient. Throwing random yeast products into a ration without understanding the underlying biology is an expensive miscalculation. We have three distinct yeast classes. Live yeast are living microorganisms consuming oxygen and producing metabolites. The cell wall offers zero biological activity. These inactivated structures, moss and beta-glucans, provide physical binding. Yeast culture is a stable fermentate, delivering B vitamins and enzymes without living cells. Achieving a high return on investment requires identifying the exact physiological bottleneck your animals are facing and matching it directly to either biological activity or structural binding. In poultry operations, birds grow incredibly fast at high densities. This specific environment creates intense gut stress and extreme vulnerability to bacterial pathogens. Attempting to solve this with live yeast fails in standard production. Pelleting poultry feed requires temperatures above 80 degrees Celsius. That heat destroys the living yeast cells long before the feed ever reaches the bird's beak. The yeast cell wall survives pelleting entirely intact. Because it is already inactivated, it withstands high heat and focuses entirely on physical pathogen control within the gut. The cell wall is a physical trap. Its MOS structures bind directly to pathogens like Salmonella, blocking intestinal adhesion. Simultaneously, beta-glucans bind to macrophage receptors, triggering a surge in cytokine production that stimulates immunity without a single living cell. For broilers, these mechanisms cut necrotic enteritis mortality in half, while improving feed conversion ratios by up to 6 points. In layer hens, the cell wall drives a 30 to 50% reduction in Salmonella shedding. It secures crucial food safety metrics while simultaneously routing more calcium into eggshell strength. For breeder hens, the stakes are generational. Pathogens must be controlled before they breach the egg, making the prevention of vertical Salmonella transmission the top priority. Investing $4 to $8 per ton of feed in yeast cell walls for breeders boosts total hatchability by up to 4%. That delivers a verified 10 to 20 to 1 return on investment. In monogastric animals, trapping pathogens and fortifying the immune system physically solves the primary cause of mortality. Structural binding mathematically outweighs the need for biological fermentation. Move to dairy and beef cattle, and the entire biological equation flips. The primary bottleneck is no longer pathogen control in the lower gut. It is the raw fermentation power of the rumen. Feeding yeast cell walls to a high-producing dairy cow entirely misses this fermentation bottleneck. The structural components offer immune support, but they do nothing to extract more energy from the animal's feed. Ruminants require the active, biological engineering provided exclusively by rumen-specific live yeast. This chart tracks rumen pH. High-concentrate diets push pH down into dangerous subacute ruminal acidosis. Live yeast acts as a biological scavenger, buffering the acid and lifting pH back to optimal zones. This stabilized environment accelerates fiber-digesting bacteria, driving up fiber digestibility. For dairy producers, extracting this extra biological energy translates to an additional 1.5 to 2.5 kilograms of milk per cow per day. That guarantees a verified 5 to 7 to 1 economic return. In the beef feedlot, buffering that same acid prevents liver abscesses and consistently drives up average daily gain on heavy grain diets. If live yeast is too expensive or cannot survive your facility's storage conditions, yeast culture provides a viable alternative, delivering modest rumen support through stable fermentation metabolites. Turning complex raw forage into usable milk and beef is the foundation of ruminant production. Supplying living biological activity to the rumen is the only way to maximize that conversion. However, there is one strict exception where these completely separate biological rules overlap: the extreme, acute physiological stress of transition. When receiving calves enter a feedlot, the physical strain of transport disrupts their rumen fermentation and simultaneously crashes their immune system, leaving them highly exposed to bovine respiratory disease. Deploying live yeast alone in this scenario stabilizes the rumen, but it leaves the compromised immune system entirely undefended against respiratory pathogens. Stressed cattle require a stacked combination strategy. Dosing live yeast repairs digestive fermentation, while yeast cell wall beta-glucans force the immune system to activate. This synergy reduces respiratory morbidity by 40%, keeping average daily gain strictly positive through the high-risk window. This exact combination strategy scales to poultry. Stacking live yeast microbial modifiers with cell wall pathogen binders is the premier method for defeating severe necrotizing enteritis in completely antibiotic-free broiler systems. When an animal faces multiple cascading failures at once, stacking complementary yeast mechanisms becomes a mathematically justified insurance policy. Here is a quadrant chart mapping the exact decision framework based on the biology and economics we've covered. If you are raising poultry or breeders, your priority is pathogen optimization. You belong strictly in the yeast cell wall quadrant. If you are managing dairy or beef cattle, your goal is yield optimization through fermentation. You belong in the live yeast quadrant. And if your animals are enduring severe stress, you target the center, applying the combination of both additives. However, correctly identifying the category will not protect your return on investment if the product specifications are hollow. Reject any live yeast product that lacks a guaranteed viable colony-forming unit count or missing heat stability data. For cell walls, reject anything containing less than 20% beta-glucans or showing high crude protein levels, which indicates incomplete, sloppy separation. Evaluate the biology, verify the specifications, and follow the definitive rule. For poultry, feed the cell wall. For dairy, feed the live yeast. For stressed animals, feed both.